Okay, so today's concept is going to be concepts of integrals and approximating the area underneath the curve. So, to start off, you have to understand what the idea behind an integral is. So, if you have some boundaries, a and b, and you have some function, just call it f of x or y, whatever you want to call it, then the integral, what it does is that it evaluates the area that's underneath this curve between those boundaries a and b. So that's not so easy for a complicated function, because you could imagine that, if this was just a square, it's pretty easy to find the area of that. But if you have some function that is very sharp and does weird things, and you want to find what that area is between those 2 points, not so easy. So the idea is that what you would do is fundamentally, in order to get this area, is that, well, the simplest thing to calculate the area of is a rectangle. So, once again, between your points A and your points B, if you have some function like that, what you do is we essentially break them up in the tiniest little rectangles all the way up. And then what you do is essentially what you're going to do is you're going to sum up the area of all of these rectangles in between there, and then that gives you an approximation of that area that's underneath that curve. So the area in the region can be found by approximating the limit of the areas of each individual rectangle. So you're going to have n amount of rectangles, and you're going to sum it up. So this area is going to be equal to the limit of the area of the nth rectangles as n approaches infinity. Because what happens is that, well, think about if you only had, let's say, 2 rectangles in this whole thing. You have some function, and you only have 2 rectangles that cover the whole thing. That doesn't give you a very good approximation, because now you have all this, you find this area underneath here, but now you have all this area up here that's not part of your approximation. So it makes it easier if you have a larger number of rectangles, because then it becomes more accurate. So the formula for this is pretty simple when you think about it. Okay, it's going to be very straightforward, because you're taking a limit as n approaches infinity, but what each rectangle is going to represent is simply, well, what is the area of rectangle? It's the height by the width. So if we know the width to be some difference in x, then all we're going to have to do is multiply fx, oh, that's not an n, this will be some integer x from however many, from 1 to whatever n we choose, and multiplied by the width. So that there, same thing, and here's your width. So what you want to do is, before, since we're using ith integers, it would essentially look more like this, and I'll write this out again. x1 will be plus f of x2, because you're taking the sum all the way till fxn delta x. Okay, so what we want to do now is we want to approximate the area underneath one of these curves. And we're not going to actually go ahead and evaluate this limit, but we have a function f of x is equal to sine x, where x goes from 0 to pi. Okay, so this is pretty simple. We're just going to take this here, and we're just going to plug it into the formula that we had before. And so we want to know what that area is. So we're going to take the limit as n approaches infinity of x1 delta x plus, and that's going to go all the way to sine x of n delta x. Alright, so we know that the delta x is just the spacing, so it's going to be that a value, or your x final value, so the b value, I mean, minus the a value, or your x initial value. So to keep this in simplistic terms, just because we've already used an xi, we'll call this b and a. Divide that by n. And you can see here that this is going to be pi minus 0 divided by n. Therefore, delta x equals pi over n. And the reason you're dividing by n here is because you have that n amount of rectangles. So, when you want to find x of I now it's going to be a value, or your x naught value, plus the ith integer of the difference in x. So we've already determined that delta x, as we have it written right above here, is this. And we know that a is equal to 0. Or x naught, I guess, whatever we want to call that. That's given. Therefore, this is going to equal I over n. And we're going to take this